Good evening. I'm so glad you've arrived. Take a moment to let the noise of the day fall away, the hum of traffic, the quick pace of thought, all of it softening now into stillness. The room is dim, the air calm, and you can simply be. Tonight, we'll drift together through the quiet chemistry that shapes our world, the gentle reactions that glow unseen in everything from candlelight to sleep itself. The warmth that curls through your body, the calm that rises as you breathe, even the dreams that wait just beyond waking, all are threads in a great, slow pattern of transformation. We'll follow those threads without hurry, letting the science unfold like a story told beside the hearth, familiar, steady, and kind. And if this moment of rest feels like a place you'd like to return to, you can softly like or subscribe so the next quiet evening finds its way to you again. Now, rest your thoughts. The night has work to do, and it begins gently with you here. Imagine your hand resting open in the dim light. There's something small resting there, maybe a spoon that still holds a trace of warmth, or a fallen feather, or the last half of a cookie you meant to save for later. Now imagine cutting that little thing in half, then in half again and again, until your mind can't quite follow the scale anymore. The pieces grow so small, they slip through what your eyes can imagine. If you could keep dividing, keep chasing the smaller and smaller, you would eventually reach a point where the thing you began with no longer exists as itself. What's left is something more fundamental, an atom, the quiet seed of everything that takes up space. Every bit of the world is made of these invisible grains. Your pillow and your teacup, the wood of your desk, the air that brushes against your skin. Even you. You are a gathering of atoms, a murmuring congregation of tiny particles arranged just so, forming a person who breathes and thinks and dreams. An atom is mostly empty, yet it carries a kind of invisible order. At its heart sits a small, dense center called the nucleus. That is where the heavy parts dwell, the protons and neutrons pressed close together, like old friends huddled around a small fire. Around them drift the electrons, the quick and restless ones, moving through space in patterns that shimmer more like fog than orbits. People often imagine atoms as tiny solar systems, but that picture isn't quite right. Electrons do not circle the nucleus in neat little paths. They are not dots on strings. They are clouds, soft regions of possibility, where we can only guess where one might be at a given instant. They appear and fade, like a thought half remembered, always just beyond reach. The nucleus, though, is steadfast. Protons carry a positive charge, neutrons carry none at all. Together they make the heavy core, the patient center that gives an atom its identity. The number of protons decides what the atom will be. One proton makes hydrogen the simplest of all, the first note in the universe's long song. 6 protons make carbon, the foundation of everything living and familiar. Add one more, and it's nitrogen. Subtract one, and it's boron. Change the number, and you change the story. Neutrons, the silent companions, keep the peace. Without them, the protons, all with the same positive charge, would push away from each other violently. Neutrons calm that quarrel, holding the core together with quiet diplomacy. Outside this dense center, the electrons dance. They are the nimble ones, the light bearers, each carrying a negative charge. They move in shells, layers of energy wrapped around the nucleus, like invisible rooms in a house made of probability. The closer the electron stays to the center, the less energy it holds. Those farther away shimmer with more, as if excited by the idea of distance. If you could somehow enlarge an atom until its nucleus was the size of a pea, the nearest electron would be hundreds of feet away, a small, trembling thing in a vast arena of emptiness. Which means that everything you touch, everything that feels solid beneath your fingers, is mostly empty space, held together by invisible forces. You and the chair beneath you, the walls around you, the ground under your feet, all of it is a vast quiet, stitched together by electrical attraction. And yet, within that emptiness, there is structure. Each atom carries a quiet rhythm, protons and electrons balanced in a steady conversation of charge. That dance is what makes the world appear solid, what allows warmth to flow, light to shine, sound to travel. A grain of sand holds more atoms than there are stars in the visible universe. Imagine that. Every handful of earth, every breath of air, more crowded with smallness than the sky is with stars. And still, each one obeys the same patient laws. They join and part, share and steal, cling and release, all to form the things we see and hold and are. Some atoms prefer solitude, like helium, light, and aloof, happy to float free without binding to anything. Others, like oxygen, are social by nature, eager to bond, always reaching for partners. Hydrogen, carbon, you could almost picture them at a quiet gathering. Helium drifting at the edge of the room, content in silence, while oxygen and hydrogen spin together across the floor, creating water, the gentle chemistry of life itself. But not every atom is calm. Some are unstable, their centers too crowded or too light, their energy too restless. These are radioactive, and over time, they change their hearts, breaking apart, releasing energy in small bursts. From that slow, invisible decay comes warmth in the core of our planet, power in distant stars, the slow ticking of time itself in ancient rocks. Even instability finds its purpose in the grand design. Through centuries of patient observation, humans have come to understand much of this invisible dance. We've learned how to predict it, to shape it, even to use it building medicines, materials, and machines that rely on the quiet cooperation of atoms. But the deeper we look, the more wonder we find. Every atom has a personality, a place in the periodic table, that great tapestry of order you might remember from school. Squares filled with symbols and numbers. It's more than a chart. It's a map of the universe's characters. Some elements are sociable and quick to bond. Some are stubborn, keeping to themselves. Some are heavy, rooted in stillness. Others are wild and reactive, drawn to flame and spark. Together, they form the language of creation, the alphabet of matter. And beneath that quiet order, something stranger hums. The rules of the quantum world bend and shimmer. Particles behave like waves, and waves behave like particles. An electron can be in two places at once, or in none that we can name. The simple act of watching can change what it does. Science, at its core, becomes poetry here, not because it abandons reason, but because it reaches the place where reason must share space with mystery. Atoms do not think or feel, and yet through them, thought and feeling exist. They are unaware of us, and still they make us. Every dream, every breath, every heartbeat is their work. The same invisible architecture that builds the stars also builds your body, your voice, your smallest sigh. And at the center of all that quiet work are the electrons, the restless hearts of the atom. Light as nothing, nearly 2,000 times smaller than a proton, yet endlessly important. They are motion made real, energy given shape. If the protons and neutrons are the patient stones of a temple, electrons are the flickering lanterns that fill it with color. They rush and tumble and leap when touched by light or heat. They slip between atoms, forming bonds, breaking them, sparking reactions that make life possible. In metals, they flow freely, a shimmering crowd of shared motion that carries electricity and gives the surface its shine. In gases, they cling tightly, glowing when nudged by energy, the same principle that lights the aurora, the neon sign, and the stars themselves. When an electron absorbs energy, it leaps upward, away from its usual place, but it can't stay there. It falls again, and as it does, it gives back the light it took. Every flame, every color in a firework, every distant glimmer in the night sky is an echo of that fall. The universe paints with electrons. Even the colors you see now, the deep blue of night, the soft gold of lamplight, exist because electrons choose which wavelengths to reflect and which to keep. A strawberry looks red because its electrons reject most other hues and return the red to your eyes. A leaf's green is the same kind of quiet decision, a conversation between sunlight and matter carried by electrons too small to see. They are also the reason your body moves and thinks. In the brain, electrons travel through neurons like sparks across a field of grass, carrying each thought, each memory, each small wonder. Every heartbeat, every blink, every dream begins as an electric whisper passing from one place to another. Yet, for all we know, electrons remain elusive. They are neither fully here nor there, neither wave nor particle, but somehow both. They slip through barriers, vanish, and reappear, defy the simple lines we try to draw around them. The closer we look, the more the boundary between certainty and mystery blurs. And maybe that's what makes them beautiful, not just what they build, but how they remind us that even the smallest things contain infinity. The world that feels solid beneath your hand is really made of patterns, of clouds of probability, holding shape for just a moment before changing again. The spoon you lift, the air you draw in, the thought forming quietly behind your eyes, all born from the same restless shimmer of electrons, circling, leaping, never still. So, as you breathe now, remember this: you are made of motion and light, of spaces held together by invisible threads of attraction. You are a pattern of atoms, each one its own tiny cosmos, humming with energy, never fully at rest. Every story begins there, in that dance too small to see the smallest somethings that make up everything. And when those atoms meet, they do what we all do when we find ourselves in the vastness. They reach for one another. If atoms could feel, their bonds would be their quiet forms of companionship. Some hold tight and never let go. Some share everything with gentle balance. Others drift together in shimmering gatherings where no one quite remembers who brought what to the table. However different their unions seem, all bonds begin from the same longing, the wish for stability, the urge to rest in calm after the constant motion. Every atom wants to settle into its softest state, to find a balance between holding and letting go, to be, for a moment, at peace. When two atoms find that peace together, it's called a covalent bond, a sharing so gentle it almost looks like trust. Picture two children splitting a piece of fruit, not one hoarding and one begging, but both offering, both tasting. Each brings something small, an electron or two, and together they create a shared orbit, a soft circuit of belonging. Hydrogen, and oxygen do this dance to make water. Each hydrogen brings one tiny piece, oxygen offers two, and suddenly the puzzle locks into place. That simple gesture gives rise to one of the universe's quiet miracles. Because of that balanced shape, water clings to itself, stretches into droplets, carries minerals, dissolves mountains, and fills our veins. All of it because a few atoms decided to share. But not every story is so polite. Sometimes, one atom wants more than its neighbor can spare. That's when an ionic bond begins a bold exchange instead of a mutual hold. Imagine one hand giving up a coin it doesn't need and another clutching it gratefully. Sodium has one restless electron it's ready to let go. Chlorine longs for just one more to complete its circle. The moment they meet, the trade is done. Sodium gives, chlorine takes, and both become charged opposites drawn together like magnets. They fall into a tidy embrace, arranging themselves into crystalline stacks that catch the light. That's salt, the taste of stability, built from an act of imbalance that resolves itself in perfect order. The beauty of chemistry is that even greed can lead to grace when the balance of charge is restored. Then there are metals, the communal souls of matter. Their bonds are not private pairings but shared gatherings, where electrons wander freely among many hosts. Picture a long table under warm lamplight. Every atom setting down its offering, none keeping count. The electrons drift between them in an easy current, a metallic sea that belongs to all. That wandering freedom is why metals shine light, bounces through the cloud of shared electrons, and scatters outward in a smooth gleam. It's also why they bend without breaking. When hammered or stretched, the atoms shift softly past one another, cushioned by the same sea of motion that holds them together. And it's why electricity flows through copper wires so gracefully. Each current is just electrons wandering home. Why do atoms do any of this? Share, steal, or contribute to the crowd? The answer, as always, is energy. Every connection is a sigh of relief. When an atom bonds, it releases what it no longer needs. It drops into comfort, like a body finding its place in a bed. Alone, atoms hum with restlessness. Together, they quiet down. The ones that stir most easily are those with unfinished edges, the valence electrons, the outer shells left wanting. Hydrogen, with just one, reaches out to complete itself. Fluorine, missing one, reaches two. The pull between them is inevitable, like two half notes resolving into harmony. Some bonds, like those in diamonds, are impossibly strong. Each carbon connected to 4 others in a lattice so perfect it can slice through steel and still shine. Others are delicate as breath. Between water molecules, tiny attractions form hydrogen bonds, they're called. They are not full partnerships, just whispers of affinity. But they are enough to let water bead and ripple, to hold a spider on the surface of a pond without breaking the skin. Bond strength depends on how tightly each atom clings to its share. Some are possessive, others generous. Fluorine is the most insistent of all, its pull on electrons so fierce that it wins every argument. At the opposite extreme sit atoms like cesium, calm and easygoing, letting their electrons wander without protest. This tug-of-war between greed and grace determines whether a substance shatters or flows, melts or sparks, endures or changes. Whenever a bond forms, energy slips out quietly, an exhale of warmth, an exothermic sigh. When bonds break, energy is drawn in again, an endothermic breath. This is why lighting a fire takes effort. First, you must feed in energy to break the old bonds in wood and air. But once they snap, new ones form. and heat rushes out like laughter. The flame you see is the record of that trade, destruction, and creation happening at once. Energy changing hands. Every reaction, no matter how small, is a negotiation. Bonds break, new ones form, energy flows. Sometimes it's patient, like rust blooming across a gate, a slow rearrangement of metal and oxygen under rain. Sometimes it's sudden, the crack of a firework, 1,000 bonds breaking and forming in a single heartbeat, light spilling across the sky. Both obey the same logic. All that changes is tempo. Even your body hums with this rhythm. Every heartbeat, every thought, every breath depends on the making and breaking of bonds. Inside you, proteins twist into perfect shapes, held by covalent and hydrogen bonds alike. DNA strands win together, their base pairs linking in quiet precision. Enzymes embrace molecules for just a moment, helping them meet and part again. The pulse of life is nothing more than chemistry arranged beautifully. Energy is the unseen conductor of this symphony. It moves between atoms like currency, paying for each transformation. But reactions rarely start on their own. Even when the ingredients are eager, they wait poised, but unmoving until something small tips the balance. That first nudge is what chemists call activation energy, the minimum push needed to get things going. Think of a match. Within its wooden stick and tiny red head lies everything needed for fire: oxygen, fuel, potential. But they sit in quiet agreement until friction wakes them. The scrape against the box adds just enough heat, just enough vibration to shake the molecules out of their comfortable arrangements. Old bonds stretch, snap, and rearrange into new ones, releasing their stored energy in light and flame. Without that spark, the match would remain still forever. Molecules, it turns out, are lazy by nature. They stay as they are until coaxed by energy to move. Activation energy is that invitation, sometimes gentle, sometimes forceful, to begin again. Imagine a boulder resting in a valley. To roll to the next one, it must first climb the hill between. That climb is the activation barrier. Once it crests the top, gravity takes over, and the rest is easy. Reactions work the same way. Some hills are low, easy to cross. Others are tall and stubborn. That's why sugar can sit in your pantry for years untouched, while gasoline flares up at the smallest spark. The chemistry is there. The difference is the cost of starting. Once a reaction begins, energy flows in one of two directions. Some processes absorb energy: endothermic reactions. They are the quiet kind, always hungry, always drawing warmth from their surroundings. Think of photosynthesis, plants gathering sunlight, using it to coax carbon dioxide and water into sugar. Without that steady light, nothing happens. Or the instant cold pack in a first aid kit, water and salt meeting, stealing heat from your skin to fuel their change. The chill you feel is simply warmth, leaving you, feeding the reaction. Then there are the generous ones, exothermic reactions, that give energy back. Combustion is their most radiant form. Light a candle, and you are watching stored energy spill out, wax and oxygen joining, forming carbon dioxide, water, and heat. The flame is the release of everything that was waiting in stillness. Your own body burns, too, though softly. Every cell is a small hearth where food meets oxygen and transforms. The sugar in a bite of fruit becomes motion, warmth, thought. The reactions are tamed and measured, step by step, so that you do not burst into flame but glow instead. alive with controlled energy. Some reactions can move both ways, depending on what the world asks of them. Water rising into vapor takes heat. Vapor falling into rain gives it back. The same molecules, the same dance, just a change in direction. Even the quietest transformations share a secret with the loudest explosions. It's all a matter of speed. A pile of leaves rotting over a season is performing the same kind of chemistry as those same leaves in fire. The rearrangement of carbon, hydrogen, and oxygen. The difference is rhythm. Slow becomes stillness. Fast becomes light. And sometimes there are helpers, catalysts, that make the climb easier. They don't change the destination, only lower the hill. They are matchmakers of the molecular world, never consumed by the reaction, always smoothing the path for others. In living things, these catalysts are enzymes, subtle and precise. Without them, your body's chemistry would crawl, food would sit undigested, thoughts would never fire, life would slow to near stillness. Enzymes whisper to atoms, now, meet, and they do. This idea that reactions depend on small thresholds of energy also explains why some substances are dangerous. When a molecule is already perched high on the hill, it doesn't take much to send it rolling. A bit of heat, a spark, even a touch of sunlight can start a chain of reactions that races downhill uncontrollably. That's what makes explosives fierce and why volatile chemicals are kept cool, away from light and warmth. Energy, if left to wander freely, loves to rearrange the world. Even medicine listens to this rule. Many drugs rest in the hush of refrigeration, their chemistry sleeping, their reactions paused on the edge of beginning. A small rise in warmth could wake them, send their molecules tumbling into change. The warnings printed on cans, "Keep away from heat," are quiet reminders of that truth. Every substance holds a threshold, an invisible hill of energy it must climb before it can become something else. Hold it cool, and it dreams in stillness. Warm it, and the dream stirs, ready to unfold. But not all chemistry is patient. Some of it lives in quick tempers and vivid moods. Acids and bases are the emotions of matter, the temper and temperament of the chemical world. When they arrive, stillness rarely lasts. They make metals fizz, turn colors wild, and send cabbage water swirling into purple storms. They appear as opposites, yet they are really partners in motion. One giving, one taking, both leaning toward the same calm center, forever searching for balance after their brief flashes of passion. To understand them, it helps to begin with water, that quiet stage where everything plays out. Even when water looks perfectly calm, its molecules are never truly still. They pull and release, trade tiny pieces of themselves, forming and reforming in a ceaseless, invisible rhythm. A few water molecules split apart, just for an instant, into a pair of ions. One positively charged, the hydrogen ion, and one negatively charged, the hydroxide. Then they find each other again, and all seems serene. It's a whispering equilibrium, happening billions of times in a single drop. An acid is simply a substance that tips that balance by offering more hydrogen ions to the water, a generous, sometimes over-enthusiastic donor. A base does the opposite. It either removes those hydrogen ions or releases hydroxide ions that quietly neutralize them. Between the two lies the spectrum of possibility, what chemists measure as pH, a scale from 0 to 14 that tells us how intense the push or pull has become. Pure water, right in the middle at pH 7, is the calm heart of the scale. Move downward, and you enter the world of acids. Lemon juice at 2, vinegar at 3. Stomach acid fierce and bright at nearly 1. Rise upward, and the bases take over. Baking soda around 9, soapy water near 10, bleach towering above at 12 or 13. Each step is 10 times stronger than the last, a quiet, exponential climb. What seems like a small number shift is, in truth, a great change in temperament. Acids are lively because of their gift-giving nature. The hydrogen ion, tiny, charged, and eager, darts through water like a spark, ready to latch on to anything that can receive it. That spark can alter molecules, speed reactions, or burn through barriers, which is why strong acids demand respect. Bases are calmer, but no less powerful. They gather those sparks, binding them up, restoring the stillness. Every reaction between acid and base is a negotiation, a subtle tug of ions finding where they belong. You can feel this chemistry at work inside yourself. In your stomach, acid unravels the meals you eat, breaking proteins into simple threads, dissolving what needs to be digested. Then, as the food moves onward, your pancreas releases a soft tide of bicarbonate, a gentle base to quiet the storm, to make the path safe again. It's a careful harmony. Too much acid and the tissues burn. Too little and digestion falters. Your body is a chemistry lab, run with astonishing grace. Even in the kitchen, acids and bases have their daily rituals. Lemon juice wakes up the dullness of food, vinegar softens meat, yogurt thickens and curdles milk into cheese. Bases play supporting roles, baking soda releasing carbon dioxide when it meets an acid, filling bread with tiny bubbles of air. Without that brief, joyful reaction, a loaf would stay heavy and dense. Chemistry, at its heart, is cooking with purpose. Sometimes, acids and bases meet as rivals who end up shaking hands. This is called neutralization, a truce written in water and salt. The acid donates its hydrogen ions, the base receives them, and what remains is calm. Vinegar and baking soda perform this peace treaty with fizzing joy, carbon dioxide escaping like laughter. It's harmless, elegant, and deeply satisfying, a small act of balance made visible. But the same principle, handled carelessly, can turn dangerous. Pour vinegar into bleach, and the story changes entirely. The acid drives the reaction too far, and the air fills with toxic gas. In chemistry, even opposites must learn boundaries. Acids and bases aren't just about bubbles and burns. They change the way molecules behave. They bend structures, open paths, or close them off entirely. Inside the body, pH governs life itself. Enzymes, the delicate workers that build and break, rely on a narrow range of balance. Too much acidity, and their intricate shapes unfold. Too much base, and they twist into useless knots. Your blood holds steady at a pH near 7.4, a number so precisely guarded that a shift of even a few tenths can bring harm. Life exists within that fragile neutrality, a reminder that survival is an act of balance. Yet the world beyond us stretches that rule in remarkable ways. In boiling volcanic pools where the pH plunges to near zero, acid-loving microbes thrive, turning what would dissolve most life into their home. In alkaline lakes where the water could strip skin, other creatures flourish, their chemistry rewritten to suit the extremes. Life, it seems, refuses to be confined by comfort. But our wider environment is not immune to imbalance. When rain carries sulfur and nitrogen from smokestacks, it turns acidic, softening stone, wounding forests, and draining the life from lakes. When the sea absorbs too much carbon dioxide, its pH slips lower, and the shells of marine creatures begin to thin, their strength dissolving grain by grain. A small change in chemistry becomes a great change in life. What happens invisibly, ion by ion, ripples outward until coral reefs fade and ecosystems falter. In industry, acid-base chemistry runs quietly beneath almost everything we make. In the battery that starts a car, sulfuric acid releases energy through a controlled cascade of reactions. In dye houses, acids fix color to fabric. In cleaning, bases lift grease from metal and glass. Every sparkle, every stain removed, every engine hum owes a debt to hydrogen and hydroxide, to the endless exchange between giving and taking. And there is beauty, too, in how we see this dance. Indicators, those clever pigments that shift with pH, reveal what's otherwise invisible. A strip of litmus turns red in acid, blue in base. Phenolphthalein blushes pink when the balance tips toward alkalinity. Even cabbage juice, humble and homegrown, runs through the spectrum like a painter's palette. Red, purple, blue, green. Each color is a moment in the tug-of-war between opposites. Behind all the fizz and color lies a deep serenity. The story of acids and bases is not one of conflict, but of conversation. One side offering, the other accepting, until a steady peace emerges. It's the same logic that keeps your blood balanced, your oceans alive, your bread rising. Chemistry's quiet truth is that opposites, when handled with care, create harmony. And while that balance hums inside the smallest droplet, it also governs the great stage of reactions, the motion of molecules shaped by heat and pressure. Because temperature and pressure are the unseen hands that set the pace. They decide how quickly molecules move, how often they meet, how eagerly they change. They are the invisible choreographers of chemistry, raising or calming the rhythm of matter's dance. Even in stillness, everything moves. Inside the wood of a chair, inside the ice in your glass, atoms vibrate with tiny quivers of life. Heat makes them restless, cold slows them down. The faster they move, the more they collide, and collisions are where reactions begin. Picture a room full of quiet people. When the music is soft, they drift, rarely touching. But when you turn up the song and offer them warmth, they start to dance. Molecules behave the same way. Add heat, and their energy rises. They spin faster, strike harder, more often, and sometimes with just the right alignment to break bonds and form new ones. That's why cookies bake faster in a hot oven, why milk sours in summer air, why your heartbeat quickens with fever. Heat gives atoms courage. It overcomes the small barriers that keep them still. Every reaction has its threshold, the amount of energy needed to begin. Raise the temperature, and more molecules cross it. Lower it, and they wait in patience. Pressure, meanwhile, shapes space itself. In gases, where particles float far apart, pushing them closer makes collisions more likely. Imagine a wide meadow filled with wanderers. They might never meet. Squeeze that crowd into a small room, and encounters become inevitable. The same is true for molecules. When we compress them, they cannot avoid each other. They meet, connect, react. In the vastness of the atmosphere, pressure falls and rises with the weather, and so does the chemistry of clouds, the forming of rain, the crackle of lightning. Deep beneath the ocean or inside the Earth's crust, where pressure grows immense, molecules behave in strange new ways. Metals melt, rocks flow, and gases turn liquid. The simplest shift in temperature or pressure can rewrite the rules of matter. Every time we strike a match, Bake a loaf, breathe, or boil a pot of tea. We are living inside that story. Heat and pressure coaxing atoms to move, collide, and rearrange. It is a cosmic dance, scaled down to the cup in your hand. And when the world feels too still, it's worth remembering. Nothing is ever truly still. Even the coldest stone hums with quiet motion. Even the calmest water carries tiny, ceaseless conversations. Chemistry never sleeps. It only slows its breathing, waiting for the next touch of energy to stir it awake again. That touch often comes in two familiar forms: warmth and weight, heat and pressure. Together, they are the twin persuaders of chemistry, the unseen hands that shape what can be and what cannot. Every nudge of temperature, every squeeze of pressure changes the rhythm of molecules, loosening some bonds, tightening others, opening doors that would otherwise stay closed. Under their influence, matter decides what face to wear: solid, liquid, or vapor, and the whole world reshapes itself in response to their quiet insistence. When particles collide, those tiny shoulder bumps you might imagine between atoms, something remarkable can occur. A bond breaks, another forms. New substances are born from the old. Increase the pressure, and those collisions happen more often. Raise the temperature, and they strike with greater force. But beyond speed, these two forces can even decide which reactions are possible and which direction a reaction will choose. This quiet truth becomes most visible in the work of human hands. In the vast halls of industrial chemistry, engineers use temperature and pressure like musicians tuning an orchestra. Each small adjustment can change the harmony, increasing yield, improving purity, coaxing matter toward balance. One of the most famous examples lives in the story of the Haber process. Picture two gases: nitrogen, the calm majority of our air, and hydrogen, light and restless. Under normal conditions, they barely notice each other, two strangers at the edge of the same room. But add heat, immense pressure, and a catalyst to guide them, and suddenly they connect, forming ammonia. That simple compound becomes the foundation of fertilizer, and in turn, the foundation of much of the food that sustains humanity. Every field of wheat, every harvest of rice, carries within it the quiet echo of that high-pressure meeting between nitrogen and hydrogen. Temperature has another role. It controls not only how fast reactions move, but how substances behave in the first place. Solids melt, liquids vaporize, gases condense, all according to the energy flowing through them. When you warm ice, the molecules loosen their grip on one another, sliding apart until water flows freely. Add more heat, and those same molecules drift away entirely, turning into invisible steam. The chemistry doesn't change, it's still H2O, but the arrangement does. Heat doesn't alter what something is, only how its pieces hold each other. Still, some reactions resist the rush of warmth. For certain fragile compounds, too much energy tears apart the very products you were hoping to form. In the delicate chemistry of life, balance is everything. Too cold, and the machinery of biology slows to a crawl. Too hot, and proteins unravel, membranes melt, and the pattern that sustains life falls apart. Every living cell is a master negotiator, surviving within its narrow band of comfort between freezing and fire. Pressure, too, has its subtleties. It is not only gases that respond. Solids and liquids, when compressed, can alter their bonds, changing texture, color, even taste. The rule, however, is most vivid in gases, where molecules drift far apart. Squeeze them, and you force their meetings. When reactions produce fewer gas molecules than they began with, raising the pressure encourages progress, drawing the molecules closer to their final form. If they produce more, the opposite happens. The system resists the crowding and slows down. Chemistry, like life, avoids congestion whenever it can. This balance of heat and pressure plays out in every kitchen, where science turns to comfort. Inside a pressure cooker, trapped steam pushes against the lid, raising both pressure and temperature. The water no longer boils at 100 degrees, but at something higher. Meat softens, beans surrender, stews melt into tenderness, all because molecules are pressed closer, persuaded by invisible physics to work faster and more kindly. Far below the sea, where the weight of the ocean bears down with unimaginable force, chemistry tells another story. Down there, pressure is so great that gases dissolve differently, reactions bend along strange new paths, and metals behave like liquids. At hydrothermal vents, where hot fluids surge from the sea floor, microbes thrive in a world of heat and darkness. They use chemistry as we use sunlight, transforming minerals into energy. Life adapts, bending to the will of thermodynamics with grace that borders on defiance. In laboratories, the same principles are tamed and measured. Glass flasks give way to sealed steel chambers, autoclaves that hold reactions at high pressures and temperatures, allowing transformations that open air could never sustain. Some processes that might take days at room temperature finish in minutes under controlled heat. Yet this mastery requires patience. Too much heat, and fragile compounds collapse. Too much pressure, and containers strain. Metal walls humming with stress. Precision becomes an art of balance, the same art that nature practices in volcanoes and stars. Chemists sometimes choose slowness instead of speed, letting reactions unfold at their own measured pace. Patience prevents chaos, reduces side effects, and keeps the dance of atoms in tune. Whether crafting a medicine or fermenting yogurt, the principles are the same. Heat gives motion, pressure gives closeness, and together they write the choreography of transformation. Even the weather answers to these rules. Warm air rises, cool air sinks. Clouds are born when vapor loses its heat and condenses into droplets. Lightning flashes as energy leaps between charged clouds, and thunder follows the air expanding so suddenly from heat that it tears sound from silence. The rumble rolling across the sky is chemistry's most dramatic applause. From the quiet stillness of ice to the trembling shimmer of steam, from the crushing depths of the ocean to the soft hiss of a boiling kettle, everything that changes in this world answers to temperature and pressure. They are the great motivators, the unseen persuaders of matter, coaxing molecules toward new forms, whispering, move, react, become. But even they do not act alone, because in chemistry, change rarely stops where it starts. Reactions are not neat one-way journeys. They are conversations reversible, responsive, capable of turning back upon themselves. What looks like an ending is often a beginning in disguise. Many reactions can move forward or backward depending on their surroundings. Molecules combine, then part, then combine again in an endless rhythm. The result is something both alive and still, a balance called equilibrium. It is not silence, but motion in harmony. Imagine a chemical tug-of-war. On one side, reactants pulling toward products. On the other, products pulling back toward reactants. At first, One side might seem to win new compounds, forming in bursts of color or warmth. But soon, the pull evens out. The rate of creation equals the rate of undoing. To the eye, nothing changes. Beneath the surface, everything does. Take a pair of invisible gases, hydrogen and iodine. When they meet, they form a deep violet vapor called hydrogen iodide. For a while, the purple deepens as the gases merge. Then, quietly, some of that vapor breaks apart again into its original pieces. At last, the forward and reverse reactions balance, each happening as quickly as the other. The color settles. The mixture reaches its calm, though the motion inside never ceases. This is equilibrium, the chemistry of compromise. A French chemist, Henri Le Chatelier, described how such systems behave. Disturb the balance, and the system adjusts to oppose the change, like a living thing trying to stay comfortable. Add more reactants, and the reaction leans forward to use them up. Remove some products, and it races to replace what was lost. Heat the mixture, and it shifts in the direction that absorbs that heat, cooling itself back towards steadiness. It's much like the way a home's thermostat keeps a room warm on a cold night. Open a window, and the furnace stirs. Close it, and the heat subsides. Chemistry does the same, a quiet intelligence written not in thought, but in the laws of energy. There's a beautiful example in the dance between two gases, nitrogen dioxide and dinitrogen tetroxide. The first is a brown haze. The second, perfectly clear. At equilibrium, they coexist, coloring the air a faint amber. Cool the mixture, and it grows paler as the gases combine into the colorless form, absorbing heat. Warm it, and the brown returns as they drift apart again. The balance never breaks. It merely shifts to accommodate the world around it. Pressure can push equilibrium too, especially in reactions involving gases. Squeeze the system, and it moves toward the side with fewer gas molecules, easing the crowding. Release the pressure, and the reaction flows the other way, filling the extra space. Even changing the concentration of a single substance will tilt the balance. Add more of one, and chemistry rushes to restore equality. Take some away, and the system gives chase to replace it. Equilibrium is not a freeze frame. It is a slow pulse, an invisible metronome, keeping time for molecules as they swap places endlessly. It's in your own body, in the exchange of oxygen and carbon dioxide, that keeps you breathing. In your lungs, where oxygen is plentiful, hemoglobin binds it eagerly. In your muscles, where oxygen runs low, the same protein releases it, the equilibrium shifting with every breath, every beat. The same principle steadies the carbonic acid in your blood, keeping your pH almost perfectly constant. When carbon dioxide rises, more acid forms. When it falls, the balance reverses. Your body is a living demonstration of Le Chatelier's quiet wisdom. Industry depends on equilibrium just as much as biology. The same Haber process that feeds the world is a reversible reaction. Chemists must coax it toward ammonia without letting it drift back to its gases. They do it with pressure, temperature, and timing, the same tools used by nature herself. Mastering that balance means efficiency, safety, and success. Equilibrium doesn't mean equal amounts of everything. Sometimes, one side dominates, the other only whispers. What matters is that both continue, their rates aligned, their energies matched. It is less like a finish line and more like a roundabout, where motion never ceases, only circles smoothly. There's something profoundly human about this principle. Nature doesn't choose extremes. It favors balance. It listens to its own feedback, adjusting, correcting, finding stability through movement. Look around and you'll see the pattern everywhere. Ecosystems balancing predator and prey, societies balancing change and rest, even thoughts balancing fear and calm. Chemistry simply shows us, with mathematical clarity, how balance is achieved. Equilibrium is not the end of reaction. It is the art of staying in motion without losing center. It's the rope in the tug-of-war going still, not because the players have stopped pulling, but because they pull with equal heart. So, when you notice condensation gathering on glass, or mist turning back into rain, or feel your own steady breath, remember this quiet law of the world. Nothing is ever truly at rest, but everything seeks its balance. Equilibrium is peace through motion, the universe finding, again and again, its perfect middle. In that balance lies a kind of hush, a pause between breaths, where the push and pull of forces cancel just enough to let stillness seem real. Yet even peace has its tremors. Every calm carries the memory of movement, and sometimes that memory wakes. There are moments when chemistry raises its voice. Most of the time, reactions whisper slow, dissolving, soft color changes, the faint warmth of transformation. But sometimes, the world's smallest actors decide to make themselves known. They release everything they've been holding in, all at once, and the result is the sudden thunder of chemistry unbound the explosion. Explosions are the language of speed. They are the same reactions we find in every flame, every breath, every rusting gate, but spoken at a pace so fast that energy has no time to hide. Heat, light, gas, and pressure burst into being almost simultaneously. In an instant, matter expands, the air trembles, and sound becomes the echo of molecules finding new forms. At its heart, an explosion is nothing more than energy released in a rush. Bonds breaking, new ones forming, gases expanding faster than the world around them can adjust. It can come from chemistry, from decompression, even from the rearrangement of atomic nuclei. But what ties them all together is the sheer speed of it, the way reaction outruns reason. Most chemical explosions begin as combustion, the ancient dance of fuel and oxygen. In slow form, it gives us candlelight and campfires, the patient warmth of life. But tighten the space, increase the fuel, or feed it with pure oxygen, and the same chemistry turns wild. Take a balloon filled with hydrogen. Alone, it floats in gentle silence. Introduce a spark, and hydrogen meets oxygen with furious affection. They bond into water vapor, releasing more energy in a breath than a candle releases in minutes. The air expands. The wave of pressure rushes outward. Sound follows, sharp and bright. That is the pattern of nearly every explosion oxidation done in a heartbeat. In combustion, the fuel loses electrons to oxygen, and new, more stable bonds form. Energy, locked inside those old connections, is freed all at once. The difference between a candle's glow and an explosion's roar is not in the chemistry, but in the tempo. One is a lullaby, the other a drumbeat. Humanity has spent centuries learning how to guide that drumbeat. Fireworks are the art of control. Small laboratories packed with oxidizers, fuels, and powdered metals, each chosen for color and rhythm. When ignited, oxygen races to meet fuel, creating hot gases that push the shell skyward. At the right height, a second ignition releases the colors: strontium for red, barium for green, copper for blue, sodium for yellow. It is the chemistry of joy, written in sparks. But the same beauty hides in greater power. Trinitrotoluene, TNT, is one of chemistry's most famous creations. Within each molecule lies both the fuel and the oxidizer, pressed into the same tiny space. Under normal conditions, it sits quietly, stable enough to be handled, carried, stored. But strike it with the precise jolt of energy it requires, and the molecules unravel in a microsecond. Nitrogen and carbon monoxide burst forth as gases, heat surges, and the solid vanishes into pressure and flame. The violence lasts only an instant, but the rearrangement is absolute. TNT is almost polite about its danger. It waits for an invitation. To wake it, you need a detonator, a smaller, more eager, explosive designed to supply exactly the right push. Once started, the reaction doesn't spread by fire, but by shock. A chain of molecular collapses moving faster than sound. In gunpowder, the reaction creeps along below sonic speed, what chemists call a deflagration. In high explosives like TNT, it races ahead as a detonation, carrying a shock wave that does most of the work. The difference is the difference between a sparkler and thunder. Explosions are not always the inventions of war or spectacle. They live quietly among us, in kitchens and factories, in mountains and oceans. A dusting of flour seems harmless until it hangs suspended in air, every grain wrapped in oxygen. A single spark in that cloud can set off a chain reaction, a blooming fireball racing through the dust. It's the same principle that makes grain silos and flour mills tread carefully, their equipment built to withstand what a baker's handful could unleash. Aerosol cans hold another kind of patience, flammable gases under pressure. Warm them too much, and the molecules inside grow restless, pressing harder against their container. If the heat keeps rising, the can bursts, releasing its contents in a rush that can ignite if flame is nearby. Even a kitchen pan can perform a sudden act of chemistry. Overheated oil ignites, and if water touches it, the story turns perilous. The water flashes instantly to steam, throwing droplets of burning oil into the air, turning flame into eruption. The physics of it is simple, the sight unforgettable. Not all of chemistry's outbursts are dangerous. The meeting of vinegar and baking soda, for instance, is a far gentler event. Acid meets base, and carbon dioxide gas escapes in a flurry of bubbles. It's a tiny, enthusiastic reaction, a miniature echo of the same principles that move mountains. The difference is scale, not soul. Elsewhere, we've turned these sudden transformations into tools. In the fraction of a second it takes an airbag to save a life, a chemical called sodium azide decomposes explosively, producing nitrogen gas that fills the cushion before your body can move forward. A small, controlled burst of energy becomes protection instead of harm, precision instead of chaos. In mining and construction, explosives move stone and earth where no hand could. Dynamite, ammonium nitrate with fuel oil, each designed not for surprise, but for reliability. Their power comes from how cleanly and predictably they rearrange themselves. A wave begins at one end, pressure moves through, and in moments rock gives way to open air. The chemistry is violent only in service of creation. Even nature writes explosions into its language. Volcanoes are Earth's own experiments in heat and pressure. Deep below, molten rock mixes with water and gases. The weight above keeps it all contained until the pressure grows unbearable. Then, in a single act, the Earth exhales ash, lava, vapor energy released from confinement into sky and sea. The same physics applies to geysers, only gentler, where water instead of magma is the restless ingredient. And among the smaller creatures of the world, evolution has performed miracles of chemical defense. The bombardier beetle carries two harmless liquids in its body, hydrogen peroxide and hydroquinone. When threatened, it mixes them in a special chamber lined with enzymes. The reaction releases heat and gas so suddenly that the mixture sprays out in a boiling jet, scalding anything foolish enough to get too close. It is an explosion by design, measured and repeatable, proof that nature understands chemistry's speed better than we do. Explosions, at their core, are not chaos. They are order moving too quickly for our eyes to follow. Bonds break, energy escapes, gases expand, all the same steps that power our metabolism and light our candles, simply accelerated until the world has no time to breathe between them. The secret to safety and to mastery lies in timing. Too slow and nothing happens. Too fast and structure collapses. But at just the right speed, energy becomes artistry. Engines turn, rockets rise, fireworks bloom. The universe itself began with something like an explosion, not of sound or flame, but of space and energy unfurling. Every star burning now, every planet orbiting, every living thing that breathes is part of that first expansion still echoing through time. The chemistry of explosions is simply that story written, small energy waiting, then released, reshaping everything it touches. And from that rush of fire, the story of another element begins. The one that holds all others together, that builds the forms of life and the bones of the world. Carbon quiet, steady, endlessly adaptable, the counterpoint to explosions' flash. Carbon doesn't shout, it builds, it listens, learns, and links. In the periodic table it sits modestly, halfway down, halfway across, but its influence reaches everywhere. Carbon is the architect of chemistry's most intricate structures, the backbone of every living thing, the thread that connects breath to soil, diamond to dust. What makes carbon special is its generosity. It can form 4 bonds at once, holding hands with up to 4 neighbors in perfect balance. That single trait gives it freedom. It can create long chains, closed rings, branching trees, delicate webs. It can form double bonds for strength or triple ones for intensity. It can stretch into simplicity or curl into complexity. Where other elements make 1 or 2 connections, carbon makes universes. This ability to bond with itself, catenation, the chemists call it, is carbon's superpower. It allows for infinite variety. No other element matches its imagination. Silicon, its neighbor below, tries, but the results are clumsy, short-lived. Carbon, by contrast, is elegant, tireless, patient. It's the weaver of molecules, the composer of life's score. Organic chemistry, the vast branch of science devoted to carbon compounds, is essentially the study of possibility. Every molecule in the living world is a carbon framework decorated with small companions: oxygen, hydrogen, nitrogen, sulfur, phosphorus, each one changing the story slightly. Add an oxygen here, and you get alcohol. Replace it with a nitrogen, and you get an amine. Rearrange the pieces, and an acid is born. Carbon is the stage upon which these costumes play their parts. The simplest carbon structure is a straight line, atoms linked end to end like beads on a thread. But carbon rarely stays simple for long. Those lines bend, loop, twist into rings. A 6-carbon ring becomes cyclohexane, a tidy hexagon of balance. Add alternating double bonds, and it transforms into benzene, a ring so stable that its electrons drift in shared resonance, a cloud of motion that gives it unusual calm. That resonance, a kind of internal harmony, appears again and again in molecules that matter. From fragrances to fuels to the pigments in your eyes, some molecules grow vast, folding into shapes of breathtaking precision. Proteins, the machinery of life, are long chains of amino acids themselves, small carbon-based pieces that twist and fold into three-dimensional sculptures. DNA, the archive of existence, is a double spiral of carbon and its companions, each twist a record of ancestry written in molecular script. Carbon's 4 bonds let it form not only single connections but doubles and triples. Double bonds shorten and strengthen, triples even more so. They change the geometry of a molecule, altering how it bends, how it reacts, how it smells, how it behaves in light. From flexible oils to rigid plastics, these differences trace back to how carbon chooses to share its electrons. Even with the same atoms, carbon can write multiple stories. Compounds called isomers share identical formulas, but different arrangements, like the same melody, played in a different key. Butane and isobutane both read as C4H10, yet one burns smoothly, while the other evaporates quicker. Rearrange the furniture, and the room feels new. Carbon also explores symmetry and reflection. Some molecules come in mirror image pairs, identical in structure but not in effect. One can heal, the other harm. Nature recognizes one hand, but not the other, a reminder that even at the molecular scale, orientation matters. The gentleness of a medicine and the danger of its twin can hinge on how carbon's bonds twist in space. Out of this endless flexibility rises life. Every cell in your body, every tree, every grain of sugar or drop of oil, all are networks of carbon. Proteins give form, lipids build walls, carbohydrates store energy, nucleic acids record instruction. Carbon binds them all, creating a chemistry strong enough to endure, yet soft enough to evolve. If those bonds were weaker, life would dissolve. If they were stronger, it would freeze into stillness. Carbon found the perfect middle. Even the first spark of life on ancient Earth likely began in its company. Experiments simulating early conditions have shown that when carbon compounds meet lightning and time, they form amino acids, the letters from which biology writes its words. It's as if the universe, given a little energy and patience, inevitably starts to spell with carbon. But carbon's story extends far beyond the biological. It shapes our materials, our tools, our world. Plastics, chains of carbon repeating like poetry, form everything from fabrics to spacecraft. Carbon nanotubes and graphene stretch our imaginations, combining strength, flexibility, and conductivity in ways that border on impossible. Fuels like coal, oil, and gas are simply ancient sunlight trapped in carbon form, waiting to be released. Even in pure form, carbon shows its range. As graphite, it slides easily, soft and dark, the texture of pencil lines and lubricants. As diamond, it locks into a rigid lattice so strong it can cut its own kin. Same atom, different arrangement, entirely different personality. The artistry lies in geometry, the angle of connection, the rhythm of repetition. And then there is carbon's shadow, the part that reaches beyond chemistry into the climate of our world. Carbon dioxide, one carbon bound to 2 oxygens, is simple, stable, and essential. It traps warmth, keeps our planet habitable, yet too much of it tilts the balance. The same molecule that nurtures crops and forests can, in excess, shift oceans, melt ice, and stir storms. Carbon's gift, as always, depends on moderation. For all its contradictions, carbon remains the quiet genius of the periodic table. It doesn't gleam like gold or explode like sodium. It sits humbly in soot and stone, in breath and bone, working its endless transformations. It is the playwright, the stage, the actor, and the story itself. The reason you think, the reason you breathe, the reason a rose smells and a mountain stands. Everything living, everything burning, everything built on this small blue planet, all of it begins with carbon's patience for connection. One atom linking to another still, weaving the tapestry of matter and meaning. And somewhere inside that lattice, between explosion and calm, between chaos and structure, lies the rhythm of life itself, chemistry's oldest and most enduring story. Redox. It sounds like a sleek invention from the future, a silver machine or a quiet robot built to polish the world clean. But in truth, redox is older than any star, older even than the earth that carries your breath. It is one of the universe's simplest and most constant exchanges, a quiet passing of electrons, the invisible sparks that make atoms live their restless lives. Everywhere, something changes where metal darkens, wood burns, food digests, batteries hum, or breath turns to warmth. Redox chemistry is quietly at work. It is the electricity of existence, the endless give and take of energy between matter and motion. At its heart, a redox reaction is simple. One substance gives away electrons, another receives them. That's all. But nothing happens alone in this world. For every atom that lets go, another must hold on. For every loss, a gain. The two are forever entwined, oxidation and reduction, the twin halves of transformation. The words sound like opposites pulled from a riddle. Oxidation, the loss of electrons. Reduction, the gain of them. It feels backward at first, as though reduction should mean losing something. But in chemistry, to gain an electron, a tiny speck of negative charge, is to become more negative, to be reduced in charge. A helpful whisper to remember: oil rig oxidation is loss, reduction is gain. Electrons are the currency of chemistry, the coins of the atomic realm. Some atoms clutch them greedily, others offer them freely. Oxygen, true to its name, is an eager collector. It pulls electrons toward itself like a tide pulling water to shore. Metals like iron or zinc are generous, happy to let go, content to find stability in the giving. Consider a garden spade, left outside after rain. Slowly, a reddish-brown film creeps across its surface rust. That soft crumble is a quiet redox symphony. The iron atoms lose electrons, they are oxidized. Those freed electrons drift into water, where oxygen lies in wait, ready to catch them and be reduced. The two sides meet, and new bonds form. Iron oxide, the delicate powder we call rust. It's chemistry's slow erosion, the world adjusting itself toward lower energy, one electron at a time. Rust is patient, almost tender in its destruction. But redox can also move at the speed of flame. Combustion fire itself is redox on fast forward. When a log burns, its carbon and hydrogen atoms lose electrons to oxygen. The energy released from those broken bonds becomes light, heat, and dance. The same process that warms your hearth can, in the right mix of oxygen and fuel, power engines, rockets, or explosions. Fire, breath, and rust, three faces of the same exchange, differing only in tempo. Inside your body, redox writes another story, one of control and rhythm. Each cell carries its own tiny power plant, the mitochondrion, where sugars like glucose are slowly dismantled. As bonds break, electrons are freed and pass through an intricate chain of proteins. Step by step, they flow like water over stones, their energy captured in molecules of ATP, the currency of life. Oxygen waits at the end of this journey, the final electron acceptor, catching the spent travelers and forming water as a reward. This is why you breathe not for air itself, but for the quiet reception of electrons. Without that last catch, everything inside would grind to stillness. A battery is much the same story, just written in metal and salt instead of carbon and breath. Inside every battery lies a tiny landscape of redox reactions. One side, the anode, gives up electrons. The other, the cathode, accepts them. Between them flows a current, silent and useful, powering your flashlight, your phone, the steady hum of your world. In an alkaline battery, zinc at the anode loses electrons to become oxidized. Manganese dioxide at the cathode gains them, becoming reduced. Between them lies the electrolyte, a medium that allows ions to drift back and forth, balancing the charges like a referee in an endless game. When you recharge a lithium-ion battery, you are literally running the movie backward, electrons pushed home again, materials restored to their earlier state, ready to begin the exchange anew. It's a reversible redox, a loop of giving and taking that can run thousands of times before the players tire. Plants, too, play this game, though in reverse. Through photosynthesis, sunlight strikes the green machinery inside their leaves. The energy splits water into hydrogen and oxygen, stealing electrons from one to give to another. Those electrons join with carbon dioxide to build sugar, the molecule of stored sunlight. In you, sugar is oxidized to make energy. In plants, energy is used to make sugar. Two halves of the same conversation, endlessly mirrored across the living world. In laboratories and factories, humans have learned to guide this electron traffic toward purpose. Electroplating, for instance, uses redox to coat one metal with another. A ring, a watch, a car bumper, all can be made to shine because electrons gently move through a bath of ions, depositing a thin metallic skin. Silverware gleams, steel resists corrosion, copper glows, all because of controlled oxidation and reduction at the surface. Redox reactions even work quietly in your healthcare. A blood glucose meter measures sugar through oxidation. Electrons released from glucose molecules create a current, small but measurable. Breathalyzers detect alcohol the same way. In water treatment plants, redox reactions transform pollutants into safer forms or strip them from solution altogether. Even your immune system uses bursts of oxidation to attack microbes, tiny chemical storms waged inside the body to defend its peace. At the atomic level, everything depends on appetite, how much an atom wants to keep or gain electrons. Fluorine is the most voracious of all, a relentless thief that pulls electrons from almost any partner. Sodium, by contrast, is generous to a fault, eager to shed its outer electron and settle down. The tug-of-war between these tendencies determines who gets oxidized and who gets reduced, who gives and who takes. In this language, the donor, the one who loses electrons, is called the reducing agent, for it reduces the other side. The taker who gains electrons is the oxidizing agent, for it causes oxidation. The paradox is poetic. By giving, one reduces. By taking, one oxidizes. Chemistry, it seems, understands balance even better than we do. Redox is everywhere. moving silently through every scale of existence. It powers engines and ecosystems, rusts bridges and ripens fruit, lights cities and fuels minds. It can be as slow as the fading of an iron fence, or as fast as the spark that ignites a stove. It can nourish or destroy, heal or corrode. But in every case, the story is the same. Electrons in motion, matter in conversation, energy changing hands. Each redox reaction is a small act of renewal. Atoms seek comfort, electrons seek home, and through their search, the universe keeps remaking itself. Whether inside a leaf, a lung, a storm cloud, or a star, this quiet transfer continues unending, unhurried, unstoppable. And yet, even this grand exchange would falter without help, because in the theater of chemistry, not every reaction is eager. Many hesitate. Their paths are steep, their barriers high. For these, another kind of player steps onto the stage, one who never takes the spotlight, yet makes everything else possible. These are the catalysts, the soft-spoken helpers of the molecular world. A catalyst does not burn, break, or vanish. It simply lends a hand, lowering the energy needed for change. When a reaction seems stuck, the catalyst offers an alternate route, a gentler slope. Once the reaction is done, it steps aside, unchanged and ready to serve again. It's the perfect guest, helpful, undemanding, invisible once the work is done. Think of a crowded city street where traffic crawls. The catalyst is the side alley that no one noticed, a quiet shortcut that gets you where you are going, faster and with less noise. The start and the finish stay the same, but the journey becomes smoother. In factories, catalysts are often metals, platinum, nickel, iron standing quietly as molecules rush past them. They help hydrogen add to oils, turning liquids solid, or convert toxic exhaust gases into harmless ones inside your car. Their surfaces hold molecules just long enough to bend bonds, to whisper, "Now." But the most extraordinary catalysts of all live inside you. Enzymes, intricate proteins shaped by evolution, are nature's master facilitators. Each enzyme recognizes one particular molecule, its substrate, and helps it react at breathtaking speed. They can accelerate a process by 1,000,000 or even 1,000,000,000,000 times, turning what would take years into seconds. Without enzymes, life would be impossible. Your food would linger undigested, your cells would fail to renew, your body's chemistry would grind down to silence. Every moment of living, every breath, blink, and thought depends on millions of enzymes working in perfect harmony, each one a tiny craftsman operating without rest. Each enzyme carries a pocket called the active site, shaped precisely to fit its partner molecule. When the substrate enters, it's held just right. Bonds stretch, shift, and rearrange. Sometimes the enzyme flexes around it, like a glove molding to a hand, until the reaction is complete. Then it releases the finished product and resets, ready for the next visitor. It's an elegant system of infinite patience. A simple demonstration lives in every kitchen. Hydrogen peroxide, the same liquid you use to clean a scrape, is quietly unstable. Inside your body, an enzyme called catalase protects you from it by breaking it down into water and oxygen. A single molecule of catalase can do this millions of times every second. Drop a bit of peroxide onto a piece of fresh potato or liver, and you'll see bubbles rise, oxygen escaping in real time, catalase at work. Another familiar helper is amylase. the enzyme in your saliva that breaks starch into sugar. Hold a piece of bread in your mouth for a moment, and its flavor begins to sweeten. That's chemistry happening on your tongue. Redox and catalysis working together in the gentlest of ways. Enzymes, like all catalysts, are sensitive souls. Change their temperature or acidity too much, and they falter, losing shape, losing function. A fever can unsettle them. A shift in pH can silence them. That's why your body guards its internal conditions so carefully. The chemistry of life lives in balance, perched on the edge of chaos, and enzymes are its keepers. Beyond biology, catalysts shape the modern world. The iron catalyst in the Haber-Bosch process turns nitrogen from the air into ammonia for fertilizer, an invention that feeds half the people alive today. Other catalysts craft plastics, medicines, synthetic fuels, dyes, and detergents. Zeolites, with their tiny honeycomb pores, refine crude oil into gasoline. Precious metals like palladium and rhodium choreograph reactions that would otherwise refuse to begin. Catalysts make chemistry kinder. They lower energy costs, reduce waste, and allow reactions to happen under gentler conditions, less heat, less pressure, less harm. They are the quiet engineers of sustainability. Some are even inspired by nature itself. Scientists design biomimetic catalysts, artificial molecules that imitate enzymes. They lack the complexity of life but mimic its precision, offering new ways to create medicines, recycle materials, or capture carbon from the air. The frontier between chemistry and biology is growing softer, more intertwined, and catalysts walk that line like diplomats between worlds. There are even catalysts that know when to stop self-deactivating systems that turn off once their task is done. Others respond to light, heat, or pH, awakening only in the right moment. In medicine, such smart catalysts could release drugs only where needed, reducing side effects and waste. In materials science, they may create surfaces that heal themselves, or fabrics that change color in sunlight. Catalysts are the backstage crew of the molecular theater, arranging scenes, guiding players, and making sure the story unfolds smoothly. They are rarely noticed, but without them, the show would never start. And perhaps that's their quiet lesson to us. Influence doesn't always come with noise. True transformation can come from the smallest nudge, the softest guidance, the invisible presence that makes everything else flow. In a universe built on redox, on endless exchanges of electrons, catalysts remind us that progress doesn't need force. Sometimes it just needs direction. The world moves forward not only through explosions and flashes, but through these gentle partnerships, the patient chemistry of help. And in that, chemistry once again mirrors life itself. Water is the strangest of companions. So common it hides in plain sight. So essential that nothing living can do without it. And yet so quietly peculiar that the rules of chemistry seem to bend wherever it flows. It makes up oceans, clouds, and the pulse beneath your skin. It slips between grains of soil and through the smallest spaces in your cells. And still, for something that touches every part of life, it never stops keeping secrets. At first glance, water appears disarmingly simple. Two atoms of hydrogen joined to one of oxygen, a tiny letter V floating in space. But that small shape gives rise to 1,000 wonders. The way it bends light, the way it clings to itself, the way it refuses to behave like other substances its size. Water's eccentricities begin with its polarity, its subtle imbalance of charge. Oxygen, greedy for electrons, pulls them close, while hydrogen, lighter and less possessive, is left slightly positive. Together they create a tiny molecular magnet, one side pulling, one side pushed, both in constant tension. This small asymmetry changes everything. Because of it, each water molecule feels drawn to others, forming delicate bridges known as hydrogen bonds. These are not true chemical bonds, but gentle attractions, little hand clasps that link one molecule to the next. Yet those countless small connections, flickering and reforming every instant, give water its strength. They make it liquid when other molecules of its size would float away as vapor. They let it cling to surfaces, pull itself upward through the stems of trees, and gather in drops that hold their shape like beads of glass. Hydrogen bonds also give water an extraordinary resistance to change. It can absorb great amounts of heat before its temperature rises. That's why the sea stays cool long after the sand burns your feet, why coastal climates soften the extremes of summer and winter. Water takes heat and releases it slowly, smoothing the violent edges of weather and time. It is the planet's great moderator, carrying warmth where it's needed and hiding it where it's not. Without it, Earth would swing wildly between freezing and flame. Then there's one of water's most paradoxical tricks. When it freezes, it expands. Almost everything else in the universe grows denser when it solidifies, the particles drawing closer as they settle into order. But in ice, the hydrogen bonds stretch outward, locking the molecules into an open, hexagonal pattern, beautiful, spacious, and unexpectedly light. And so, ice floats. That single quirk reshapes the world. If ice sank, lakes would freeze from the bottom up, trapping life beneath until spring thawed them, if it ever did. Instead, ice drifts on top, forming a shell that insulates the water below. Beneath that thin frozen ceiling, fish swim, plants breathe, ecosystems persist through the hardest winters. The geometry of a single molecule becomes the architecture of survival. Water's other great power lies in its willingness to mix. Its polarity allows it to pry apart the bonds of other compounds, surrounding ions and molecules, and carrying them into solution. Drop a pinch of salt into a glass, and watch invisible hands of water tug the crystal apart, wrapping each piece in a ring of molecules, turning solid into fluid. This is why the blood in your veins can carry nutrients and waste, why plants draw minerals from soil, why rivers carve their way through rock. Because of this, water is called the universal solvent. Though it has its limits, non-polar substances, like oils and fats, resist its embrace. Like dissolves like, the chemists say. Polar with polar, non-polar with non-polar. That's why oil floats on soup, why vinegar and oil part in a bottle, why soap, which carries both kinds of chemistry in one molecule, can coax grease into surrender. One end of a soap molecule clings to oil, the other to water, creating tiny droplets called micelles that wash away with ease. It's a small act of harmony, water, oil, and chemistry finding common language. Inside living cells, water does far more than fill space. It is the background and the participant, the stage, and sometimes the actor. Enzymes fold within it. DNA twists and unwinds because of its gentle push and pull. Proteins take their shape, and thus their purpose, only in its presence. Change the water around them, and they lose their form. In this way, life itself is a choreography of hydrogen bonds, with water conducting quietly from the wings. Even the oxygen you breathe is a gift from water. In the bright green cells of plants, sunlight splits water molecules apart, freeing electrons that help build sugar, the food of life, and releasing oxygen as a byproduct. Every breath you take, every flame that burns, is an echo of that original generosity. On the scale of planets, water sculpts with equal grace. It wears mountains into dust, lays riverbeds through stone, smooths pebbles into roundness. It gathers clouds, falls as rain, freezes into glaciers, melts again, and moves on. The water cycle is not a circle so much as a pulse, a steady rhythm connecting ocean, sky, soil, and living things in an endless loop. In this quiet migration, energy moves, nutrients travel, and climates are born. Chemically, water seems mild, stable, familiar, but it is never passive. It can act as both acid and base, giving or receiving protons depending on what's needed. That dual nature makes it the great mediator of reactions, the keeper of balance in cells and soils alike. It adjusts, it buffers, it makes life possible not by choosing sides, but by holding both. Yet, for all its abundance, water is a fragile luxury. Of all the water on Earth, barely a fraction of a percent is fresh and easily reached. The rest lies locked in ice, deep underground, or salted by the sea. Every sip, every raindrop, every clear stream is part of a narrow thread in the web of the world, precious, finite, endlessly recycled. That scarcity is why astronomers, searching the dark, look for water as a sign of possibility. On Mars, beneath its rust-colored dust, on Europa beneath its icy crust, on Enceladus in its plumes of vapor wherever water flows, even briefly, the question follows, could life be here too? Because water doesn't merely host life, it enables it. It stabilizes, nourishes, and connects. It carries heat, dissolves matter, and gives structure to everything that breathes. And you, too, are a vessel of that same substance. By weight, you are more water than anything else, 60%, give or take. As an infant, you were nearly 3/4 water, soft and new as a tide. Your blood is mostly water, carrying oxygen and nutrients through miles of living tunnels. Your brain is mostly water, thought flowing in liquid form. Even your bones, solid and silent, hold water in their structure. It cushions your joints, regulates your warmth, cleanses your cells. You are not separate from water. You are its continuation, shaped to hold it, made from it, moving with it. It's easy to overlook what never demands attention. But once you start to notice water, you see how impossible life would be without its peculiarities, its patience in absorbing heat, its stubborn refusal to sink, its endless generosity as a solvent. Water is a rule breaker, a shapeshifter, a quiet magician that carries the logic of chemistry and the tenderness of life in the same transparent body. For a molecule made of just 3 atoms, it holds almost all the world's grace. And beyond the shimmer of water lies the matter that gives it form, the stage on which it performs its endless dance. Matter, the word itself, sounds simple, but the reality it describes is anything but. Everything you touch, see, or breathe is built from it. The wood of your chair, the air around you, the steam from a cup of tea. Yet beneath that ordinariness lies a restless motion, particles shifting and vibrating, whispering energy from one to another in a ceaseless exchange. We're taught that matter comes in 3 forms: solid, liquid, and gas, and sometimes a 4th, plasma, for the stars. But those are only chapters in a longer story. Each state of matter is a different rhythm of motion, a different balance between closeness and freedom. In solids, the rhythm is slow and sure. Particles lock into patterns, vibrating in place but holding firm. That structure gives solidity, its calm, its weight, its resistance. Touch a stone or a spoon left in the cold, and you're feeling the quiet order of atoms held close, the strength of bonds refusing to let go. Heat them, though, and that order starts to loosen. Vibrations grow stronger until bonds stretch, waver, and break. The rigid grid softens, and the solid becomes liquid. Liquids are the mediators, neither rigid nor wild. Their particles remain close but unbound, slipping past each other in graceful confusion. Liquids hold volume but not shape. They conform, they adapt. A cup, a bowl, a cupped hand, each becomes their form for a moment. Surface tension, viscosity, capillary rise, all are expressions of the invisible forces binding them just enough to stay together. Add more energy, and the dance quickens. Molecules break free entirely, bursting apart into the open. The liquid becomes gas, particles moving too fast and too far to stay tethered. A gas has no boundaries. It fills whatever space it finds, pressing outward in all directions. The air around you is full of this motion, invisible, constant, lively. You breathe it in, and the molecules rush into your lungs, rebound, and drift out again, unchanged. Gases can be compressed, squeezed closer together, because so much space lies between their particles. Solids and liquids, already tight-knit, resist that squeeze. But a gas gives way, reshaping under pressure. It's what lets tires hold air and divers breathe underwater, what turns wind into power and sound into travel. Beyond gas lies plasma, matter's wildest state, where heat becomes so intense that atoms lose their electrons and the air turns to fire. The sun, lightning, the auroras shimmering at the poles, all plasma, all matter at its most alive. Charged particles swirl and respond to magnetic fields, their movement giving birth to light itself. Remove energy, and the process reverses. Gas condenses into liquid, liquid solidifies into ice. Water beads on grass in the cool of morning. Frost blooms on a window pane. Snowflakes grow in clouds. All these are matter slowing down, particles drawing near. Sometimes the steps are skipped entirely, solid turning straight to gas, as with dry ice. Gas freezing straight to solid, as with frost. Every change of state is simply matter responding to its circumstances, adjusting to balance the energy it holds. Temperature and pressure are the two hands guiding this dance. Heat makes particles move faster, spreading apart. Pressure presses them closer. Together they decide what form matter will take. And water, ever the rebel, finds exceptions even here. Under the blade of a skate, pressure makes ice melt instead of freeze, creating a thin film of liquid that lets the skater glide. It's physics lending its grace to motion. To understand matter is to understand that stillness is an illusion. Even the hardest stone vibrates faintly. Even the quietest air moves. Everything is in motion, only at different speeds. When the tea beside you cools, molecules slow and settle. When you breathe, gases swirl in and out, mingling your body with the atmosphere. When ice melts in your glass, it is simply matter's shifting phase, same substance, different energy. Change everywhere, but never loss. Matter doesn't disappear, it transforms. Solid to liquid, liquid to gas, energy in, energy out. the pattern repeats endlessly, a slow and beautiful rhythm that underlies everything we see. The world may look still, but beneath that stillness, the particles keep dancing. And perhaps that's the quiet comfort of it all, knowing that nothing truly ends, it only moves. Not every meeting in chemistry ends in light or thunder. Most do not. More often, things simply meet quietly, curiously, and decide to share space. They mingle for a time, dissolve or drift apart, and nothing truly new is born. The atoms remain themselves, unchanged and unbothered, like neighbors exchanging glances across a fence. This is the chemistry of mixtures, the gentler side of transformation. No bonds are broken, no sparks leap out. It is chemistry without ambition, but not without beauty, the kind that keeps your tea fragrant, your dressing suspended, your seas alive with salt. A mixture, unlike a reaction, doesn't rewrite its ingredients. In a reaction, atoms rearrange, bonds break and reform, and the result is something entirely new. Oxygen and hydrogen become water, iron becomes rust, but in a mixture, things merely coexist. Their natures remain intact. A cup of tea is one of the simplest examples. When hot water meets dried leaves, it draws out color, scent, and flavor, yet the water itself stays water. The molecules in the tea remain what they were, only dispersed, softened, carried. With the right patience and tools, you could take the tea apart again, separate the pigments, oils, and caffeine, and find nothing lost, nothing gained, only mingled for a while. That's the quiet signature of a mixture. It can be undone without heartbreak. Mixtures take many forms. Some are smooth, others patchwork. When the blend is uniform, every sip and drop identical, we call it homogeneous. Salt water is the perfect example. Salt dissolved so completely that no grain remains. The ions of sodium and chlorine drifting evenly among the water molecules. It looks pure, yet beneath the surface, a balance hums. Other mixtures are less diplomatic. They keep their parts visible and distinct, the heterogeneous kind. Think of a spoonful of granola, a bowl of soup, a vinaigrette that separates as soon as your hand stops stirring. These mixtures share space, but not uniformity. Oil beads at the surface, vegetables drift in broth, grains settle at the bottom. Time alone reveals their boundaries again. A solution is the simplest, most seamless kind of mixture. A solute fully dissolved in a solvent. In salt water, salt is the solute, water the solvent. Every molecule of salt is embraced, surrounded, hidden within the water's lattice of attraction. Solutions come in all states of matter. The air you breathe is a gaseous solution, mostly nitrogen and oxygen, with traces of others drifting invisibly. Brass, steel, and other alloys are solid solutions, atoms of metal folded together into one metallic whole. And most of the world's liquid solutions, from the sea to your bloodstream, depend on water as their solvent. Water, small and polar, is a master of mixing. Its molecules pull apart charged or polar compounds, cradling them until they vanish into clarity. But some substances resist. Oil, for instance, will not dissolve in water. Its molecules lack polarity. They have no charge for water to grasp. The water holds onto itself instead, pushing the oil aside. The two form a truce of separation, a floating layer, or droplets shimmering like marbles. This is the beginning of a suspension. Suspensions are mixtures where particles drift within a fluid, but never fully dissolve. Their pieces are large enough to scatter light, sometimes even visible to the eye. Muddy water, flour stirred into milk, orange juice with pulp, Each is a suspension, cloudy and temporary. Left alone, gravity will do its slow work, pulling the heavier parts down until layers appear. These are mixtures that must be stirred back into harmony. Between the world of true solutions and loose suspensions lies a delicate middle ground: colloids. Their particles are tiny, too small to settle, too large to disappear. Milk is one, so is fog, and even the glow of mayonnaise under kitchen light. In colloids, the particles stay afloat, scattering beams of light into soft halos, a phenomenon known as the Tyndall effect. What looks smooth to the naked eye is, under magnification, a quiet constellation of suspended worlds. Understanding these subtle differences between solutions, suspensions, and colloids is more than textbook detail. It is the logic of the kitchen, the workshop, and the body. A salad dressing, for example, is a brief act of chemistry. Oil and vinegar, left alone, will part ways, but add a spoonful of mustard or egg yolk, and the mix suddenly holds. The emulsifiers in those ingredients bind droplets of oil and water together, stabilizing them in a fragile truce we call an emulsion. That's why a good vinaigrette feels creamy. Even though it contains no cream, it's a colloid disguised as a sauce. Cooking is full of such quiet chemistry: melting, mixing, whipping, cooling. These are physical changes, not chemical ones. When you shred cheese or boil pasta, you alter form, not identity. The molecules remain themselves. But when you bake, when sugar browns, proteins stiffen, and gas bubbles rise in batter, that is a true chemical transformation. Bonds rearrange, new compounds emerge, and the change cannot be undone. A cake can never go back to being dough. Physical changes are reversible. Chemical ones rarely are. The beauty of mixtures lies in their impermanence, their willingness to be taken apart. Through simple means, filtration, evaporation, distillation, we can coax their components to separate again. Let seawater dry and salt crystals return. Pour muddy water through a filter and clear liquid reappears. Even crude oil, thick and ancient, can be separated into fuels and waxes by heating it carefully, so that each fraction evaporates at its own temperature. This ability to sort, to purify, underpins modern chemistry and modern life. Medicines, fuels, perfumes, metals, all depend on our capacity to separate mixtures precisely, to control the meeting and parting of substances. Nature does it too. Blood, for instance, is not a single fluid, but a suspension of cells, proteins, and salts drifting in plasma. Soil is a mixture of minerals, organic matter, water, and air, its structure constantly shifting with moisture and roots. Seawater carries dissolved salts, gases, and microscopic life. Even clouds, those dreamlike forms above, are colloids, droplets of water suspended in air. So much of existence depends not on chemical revolution, but on coexistence, on substances sharing space without surrendering themselves. And perhaps that's what mixtures quietly remind us, that chemistry, like life, isn't always about change. Sometimes it's about presence, about molecules floating side by side, content to remain who they are. Not every encounter must end in transformation. Some are simply about proximity, about staying close without merging, about balance between blending and separation. Every time you stir honey into tea, shake a dressing before dinner, or stand by the ocean breathing its salted air, you're surrounded by this quiet chemistry. No fireworks, No heat, no reaction. Just the steady grace of things coming together, staying themselves, and making something new only through harmony. But there's another kind of quiet, the kind that hides beneath every reaction, measured not by what happens, but by how fast it happens. Some reactions unfold faster than the blink of an eye. A match catching fire, lightning splitting air, fireworks bursting into color. Others take years, even centuries iron rusting, rocks weathering, fossils forming in stone. And some reactions barely stir at all, but all share one truth. Every chemical change has a rhythm. Chemists call it the reaction rate, the speed at which reactants become products. Sometimes we notice it without meaning to. Leave milk out on a warm afternoon, and it sours quickly. Leave it in winter's chill, and it stays sweet for days. The molecules are the same, but the conditions, the temperature decide their pace. Heat, after all, is energy. Raise it, and atoms move faster, colliding more often, colliding harder. Imagine a dance floor. At low temperature, the dancers sway lazily. At high, they spin and collide in a blur. More motion means more chance of connection, of change. Still, not every bump leads to reaction. The molecules must meet in just the right orientation, with just enough energy to climb the invisible hill between what is and what could be the activation barrier. Heat helps them reach that peak. So does concentration. Pack more molecules into a smaller space, and collisions become inevitable. A crowded subway makes for more accidental shoulders brushed than an empty one. Chemistry follows the same logic. Surface area plays its part too. The more exposed a solid surface, the faster it reacts. A cube of sugar dissolves slowly in tea. Crush it first, and it disappears in seconds. The same holds for metals. Corroding or fuels burning. The finer the particles, the faster the chemistry. Powdered spices bloom in a pan, because every grain meets heat and air. Fireworks explode with brilliance, because their powders offer more surface for reaction. Some reactions, though, are stubborn. Their bonds are too stable, their paths too winding. You can heat them, stir them, press them, and still they crawl. For these, chemistry employs its quiet specialists, catalysts. They don't change the starting or ending materials. They simply make the journey easier. They offer shortcuts, lowering the energy needed for the transformation. Nature uses them too, calling them enzymes. Inside your body, enzymes make the impossible routine. They let digestion, repair, and growth happen in seconds instead of years. Light can be a catalyst as well. In the leaves of plants, photons strike chlorophyll and set electrons in motion, the first step of photosynthesis. In an old photograph, silver compounds darken because light rearranges their structure. A beam of energy, fleeting and weightless, can start a chain of molecular decisions that last forever. Reaction rates remind us that chemistry is not just about what can happen, but how it happens. The patience of rust, the swiftness of flame, the stillness of balance. Everything that changes, from the growth of trees to the flicker of a candle, moves at its own tempo. And somewhere between the fastest flash and the slowest drift lies the rhythm of the world, quiet, constant, endlessly turning, as matter meets energy again and again in the soft choreography of time. Every reaction, no matter how grand or small, keeps time. In the quiet heart of chemistry, speed matters not because faster is better, but because pace shapes everything that follows. A reaction that runs too quickly can turn wild, dangerous, or wasteful. One that crawls, may never reach its end. The art lies in finding the tempo that suits the purpose, steady, contained, and true. In laboratories, chemists live by this rhythm. They warm and cool, stir and measure, coaxing reactions into the sweet balance between stillness and explosion. Too slow, and a factory might sit idle, waiting on chemistry to finish its work. Too fast, and the same factory could find its vats boiling over in chaos. Every beaker is a lesson in timing, every equation a test of patience. Even a kitchen follows these laws. When meat browns in a pan, the Maillard reaction, a slow, intricate waltz between amino acids and sugars, begins. At the right heat, it yields depth and flavor, that irresistible scent of roasted warmth. Too cold, and the surface stays pale. Too hot, and everything burns before the music finishes. Cooking is chemistry at human scale, an instinctive conversation with reaction rates. Refrigeration tells the same story in reverse. Chill a meal, and you slow the molecular chatter that spoils it. The fats that would oxidize, the proteins that would sour, the bacteria that would multiply, all of them drift into sluggishness, their dances delayed. Cold doesn't stop change, it just quiets it. That same principle keeps medicine stable, organs preserved for transplant, and even fossils waiting beneath stone for millions of years. Some reactions move so slowly that to us, they seem frozen in eternity. A diamond quietly reshaping into graphite, a transformation so gradual that it defies a human lifetime. Ancient organic matter, buried and compressed, becoming oil and gas, through chemical whispers stretched across geological ages. Others blaze and vanish in a blink. Hydrogen and oxygen uniting into water in a rocket's flame, energy released in an instant so fierce it could lift metal toward the stars. Understanding these rates is, in a sense, understanding time itself. Chemistry moves at its own rhythm, molecules colliding, deciding, transforming, or choosing stillness. Heat, pressure, concentration, and catalysts all tune that tempo. Every rusting gate, every bubbling pot, every ripening fruit is a kind of choreography. Billions of invisible dancers moving in measure with the world around them. There's a strange comfort in this. Not everything must happen at once. Some transformations belong to lightning, others belong to stone. Every reaction finds its right pace when the world gives it patience enough. And patience is the foundation of life's own chemistry, the slow, ceaseless work that hums beneath your heartbeat. Biochemistry doesn't sparkle or explode, it whispers. It's the quiet chemistry of breath and pulse, of dreams forming behind closed eyes. It keeps its laboratory inside you, running day and night, a soft-lit city of reactions that never sleep. No fireworks, no smoke, just the elegant precision of molecules doing exactly what they must. At its center are three familiar companions: proteins, DNA, and ATP, the builders, the archivists, and the keepers of energy. Their roles are humble, their timing perfect, their reliability absolute. Proteins are the tireless workers, long chains of amino acids folded into intricate shapes, spirals, sheets, pockets, bridges, each fold a decision written by the code of your DNA. Shape is destiny here. A twist or curl determines whether a protein becomes an enzyme guiding reactions, a scaffold giving cells their form, or a messenger carrying signals across the body. Enzymes, those specialized proteins, are life's catalysts. They make the impossible easy, lowering barriers and smoothing paths so that reactions finish in seconds instead of centuries. Without them, a single meal could take weeks to digest. DNA polymerase, for instance, is the scribe that copies your genetic library every time a cell divides. Amylase, working in your saliva, begins turning starch into sugar before you even swallow. Each enzyme recognizes its partner like a lock, meeting its key exact, deliberate, intimate. And then there's DNA itself, the grand architect of existence. A double helix of 4 bases, adenine with thymine, cytosine with guanine, spiraling upward in a code that writes every cell, every limb, every breath. It's an astonishing economy of language. 4 letters arranging themselves into all the instructions for life. Yet, the code alone is inert. It needs motion. It needs energy. It needs something to turn blueprints into being. That role belongs to ATP, adenosine triphosphate, the currency of cellular energy. Every cell depends on it. Every motion you make spends it. When ATP gives up one of its phosphate bonds, it releases a spark of energy, enough to power muscle fibers, repair tissues, or send messages between neurons. What remains, ADP, waits patiently to be recharged. It's a rechargeable battery at the molecular scale, used billions of times per second within you, never tired, never truly empty. All of this together, the folding of proteins, the copying of DNA, the cycling of ATP forms metabolism, the endless dance of breaking and building. Catabolism tears down complex molecules to release energy. Anabolism builds new ones, stitching energy into structure. Destruction and creation are not opposites here. They are partners, holding hands in perfect balance. Think of metabolism as a living city. Molecules are its citizens, enzymes its factories, ATP its currency. Streets, wind between them, full of motion and trade. Some molecules rush toward construction sites to build new tissues. Others return, carrying waste to be broken down. The traffic lights are feedback signals, switching on and off as the city's needs change. When energy runs low, the lights shift and more fuel is burned. When the streets grow crowded, they turn red and the flow slows. It's organized chaos, a metropolis humming with order disguised as noise. Take glycolysis, the pathway that splits glucose to release energy. 10 precise steps, each guided by a different enzyme. The process doesn't burn sugar all at once, it dismantles it gently, capturing the released energy in small, manageable bursts. Those bursts become ATP, the pocket-sized coins of metabolism. Then, in the citric acid cycle, the Krebs cycle, the fragments are oxidized further, and electrons, charged and eager, are passed down a chain of molecules, like a line of workers handing buckets in a fire brigade. The electron's journey creates a proton current across a membrane, and that current drives the turbine of life itself, ATP synthase, the enzyme that spins out energy as though it were weaving light into matter. From a single glucose molecule, more than 30 ATP molecules emerge enough to power an entire microscopic civilization for a moment. The elegance of it defies imagination, pure chemistry, achieving something that looks, from a distance, like intention. And yet, metabolism is not just about energy. It's repair, renewal, and response. It builds the walls of cells, mends DNA, breaks down toxins, balances hormones, fuels memory. It keeps hunger and warmth and movement in constant negotiation. Each molecule has a purpose, but none acts alone. Sometimes, though, the harmony falters. A single misfolded protein can spiral into tragedy. The prions that twist the brains of animals, the malformed amyloids that shadow human memory. A missing enzyme can leave a pathway blocked, causing compounds to build up where they shouldn't. Diseases of metabolism are reminders that even the smallest errors in timing or structure can echo across an entire organism. And still, life endures. Cells reroute their pathways, enzymes adapt, new proteins evolve to take on lost functions. From bacteria in boiling vents to creatures beneath Antarctic ice, life keeps rewriting its chemistry to match its surroundings. Biochemistry is both fragile and indomitable, a system that breaks easily and yet refuses to stay broken. Perhaps the most humbling truth of all is that the same chemistry runs through every living thing. The bacteria that live in a droplet of water and the whale that moves through the ocean both read the same molecular script. DNA is universal. ATP is universal. The genetic code itself is nearly unchanged across billions of years. Life did not reinvent itself. It refined what already worked. Biochemistry is not the chemistry of explosions or inventions. It is the chemistry of continuity. It loops, recycles, restores. It's how carbon, nitrogen, oxygen, and hydrogen, the same atoms that make stone and sea, learn to organize into something that thinks, feels, and dreams. And they do it quietly. In you, trillions of reactions happen every second, yet you hear nothing. You don't feel the enzymes working or the ATP breaking apart. You only feel life as its result. Breath, thought, warmth, motion. If you could listen closely enough, beneath the thrum of blood and the pulse of air, you might hear it, the faint hum of chemistry performing miracles without ceremony. A molecular orchestra tuning itself endlessly, keeping the lights on in the great cathedral of being. That is biochemistry. Not loud, not showy, but steady the heartbeat beneath every other heartbeat. The whispering pulse that carries life from one second to the next. And just beyond the boundaries of our bodies, that same chemistry stretches outward into the stones beneath our feet, the seas that shape our air, and the restless planet that hosts it all. Earth itself is alive with reactions, a giant cell made of continents and clouds. Beneath the crust, molten minerals stir. Above the clouds, gases mix and drift. Mountains rise and crumble. Oceans breathe mist into sky and draw it back again. To look at Earth through chemistry is to see a living rhythm written not in DNA, but in rock and fire. It's to understand that the planet's calm surface hides a ceaseless dance of elements, carbon moving between air and stone, sulfur cycling through volcano and rain, iron sinking to the core, oxygen feeding flame and breath alike. The chemistry of life is delicate. The chemistry of Earth is immense. But both obey the same quiet rule that transformation never ends. It only changes its tempo. When water meets stone, something quiet begins. It isn't the drama of fire or lightning, but a softer conversation drop after drop, molecule by molecule. In those meetings, minerals listen. Feldspar, hidden in granite for millions of years, slowly gives in to the gentle insistence of rain. The water, faintly acidic from its time in the sky, brushes across the surface and begins to take pieces with it. A bit of calcium here, a little potassium there, each atom released into the wandering streams. What begins as a whisper of rain becomes, over centuries, the slow reshaping of mountains into sand, soil, and clay. That soft breakdown is chemistry with patience, one drop rewriting the face of the world. The rain itself carries its own small story. As it falls through the air, it gathers traces of carbon dioxide, weaving a fragile acid that seeps into stone and soil. Over time, that mild solution carves grand cathedrals beneath the earth caves, where water still sings in the dark, shaping limestone into delicate pillars and spiral chambers. A landscape built not by violence but by persistence. What begins with vapor ends with valleys. And when the minerals break apart, their fragments do not vanish. The calcium and carbonate they release wander downstream, drawn to the sea. There, they meet the living architects of coral and shell. Out of the ions dissolved in water, creatures draw their armor fragile, intricate, built from chemistry that began in stone. When they die, their shells drift down like snow, layer upon layer, forming limestone once again. The planet remembers itself, recycles itself, turning death and dissolution into something strong and new. Each rock, each wave, each grain of sand is part of that same slow exchange. Water speaking with stone, life speaking with time. This conversation continues in the great rhythm of carbon, the restless traveler of the planet. Carbon drifts through air as invisible gas, rests in living leaves, hides in soil, and sleeps beneath oceans as ancient fuel. In the daylight, green things pull it in, weaving it into sugar, stem, and fruit. Animals eat and breathe it out again, completing one brief loop of the endless cycle. When life ends, microbes and fungi take their turn, returning the carbon to air and earth so it can begin again. Sometimes, a small portion escapes that quick renewal buried, compressed, hidden for eons in stone and pressure. There it waits as coal or oil, dark reservoirs of sunlight captured long ago. When we burn them, that stored breath returns to the sky as carbon dioxide, a pulse of ancient energy rejoining the present. It's a cycle not of perfection but of balance, constantly adjusting, remembering, forgetting. Volcanoes breathe carbon out from the deep mantle. Rain pulls it down again into rock. Forests and oceans trade it back and forth, each acting as a lung for the planet. Every exhale, every tide, every falling leaf is part of that chemistry of air and stone. Together they shape climate, turning sunlight and carbon into the delicate equilibrium that allows warmth and life to stay. The air itself is never still. It looks invisible, but it is alive with reactions, molecules forever, meeting, parting, and reuniting. Oxygen and nitrogen make the quiet background of every breath. But mixed among them drift others: water vapor, methane, ozone, and the trace gases that guide the weather and the seasons. Ozone forms high above, thin but mighty, shielding life from the sun's harsh ultraviolet light. That same molecule, nearer the ground, becomes a nuisance, a haze that irritates lungs and dims horizons. The same chemistry that protects can also harm, depending on where it lives. Nature's balance is always a matter of place and proportion. Methane moves through the air like a ghost of warmth, born from wetlands, grazing animals, and the deep work of microbes. It is fewer in number than carbon dioxide, but far more powerful at trapping heat. It doesn't linger forever. Sunlight eventually breaks it down, but while it lasts, it shapes the breath of the planet. Water vapor too plays its part, rising, cooling, condensing into cloud. A cloud is not just vapor. It is chemistry in motion, tiny droplets filled with ions, acids, salts, and traces of life's dust. In every bead of mist, reactions hum silently. Pollutants dissolve, minerals shift, light scatters, rain begins. Even the cleanest drop carries the memory of the sky. From a distance, Earth behaves like something alive. Its atmosphere breathes, its crust circulates, its seas exchange heat and minerals in patterns that seem to think. It isn't alive in the way we are. It has no heartbeat, but the feedbacks, the loops, the self-corrections give it a strange awareness of balance. When the air warms, weathering quickens, drawing down carbon. When the world cools, volcanic breath replenishes it. The rhythm stabilizes over millennia, not days. It's chemistry, as memory, each reaction leaving traces that shape the next. Some scientists once called this the Gaia idea, that life and planet co-evolve, each maintaining the other's harmony. Whether or not the metaphor holds, the truth remains. The earth and its living things are inseparable, each feeding, tempering, and defining the other. From deep roots to high skies, life and earth are partners in a slow conversation. Soil microbes pull nitrogen from the air, turning it into food for roots. Trees lift that nitrogen and exhale oxygen in return. Oceans absorb the planet's fever, holding vast stores of heat and carbon. Coral reefs build limestone from seawater, while mountains crumble back into that same sea. Everywhere you look, the living and the non-living exchange places stone to shell, air to leaf, leaf to dust, dust to star. Chemistry is not just what happens to the world. It is what holds the world together. The atoms in your own body have followed those same paths. The calcium in your bones once glowed in the heart of a dying star. The iron in your blood was forged in a supernova's collapse. The nitrogen in your DNA may have sparked from lightning in an ancient sky. You are not an observer of chemistry, you are its continuation. Every breath is a transaction between you and the world. Every heartbeat, an agreement with gravity and time. When you exhale, the carbon in your breath may rise, drift, and one day feed a tree that will turn sunlight into sweetness again. You are part of the circle, not standing outside it. Beyond our skies, that same language continues. In the wide quiet of space, chemistry writes slower but grander stories. There, stars act as the universe's laboratories, forging elements in unimaginable heat and pressure. Inside a young star, hydrogen becomes helium, and helium becomes carbon and oxygen. Layer upon layer, the elements stack and fuse until the core grows heavy with iron. Then, the story changes. The star collapses inward, and in that collapse comes an explosion so powerful, it floods the cosmos with new matter: gold, silver, uranium, the bones of future worlds. For a moment, one star outshines a galaxy. When its light fades, it leaves behind a cloud of potential, a nursery for everything that comes after. Between the stars, the space is not empty but filled with dust and whispers. Vast clouds of hydrogen and carbon drift for millions of years. Within their cold depths, atoms cling together, forming water, ammonia, and simple organic molecules. Each grain of cosmic dust becomes a tiny workshop, a place where chemistry continues in silence. Some of these clouds will collapse under their own weight, spinning into new stars with disks of gas and rock swirling around them. From those disks, planets are born, moons form, comets gather, and the old atoms, those fragments of previous stars, find new homes. The universe is a recycler too. Even in places that seem hostile, Venus with its sulfuric skies, Mars with its whisper-thin air, Titan, with its methane lakes, chemistry never stops. Each world runs its own experiment, guided by temperature, pressure, and time. Lightning on Jupiter ignites new molecules. Saturn's rings exchange water and dust. Comets trail their frozen tails of ancient material, leaving hints of what the solar system once was. Every planet, every moon, carries its own quiet version of the same story. Matter rearranging, seeking balance. When we look beyond our solar system, that chemistry becomes our map. Astronomers read the faint signatures of light from distant worlds, decoding the gases that veil them. In those patterns, we can tell whether there is water, methane, carbon dioxide, perhaps even the distant trace of oxygen made by life. We may never touch those planets, but through their chemistry, we can know them. And perhaps one day, somewhere, we will recognize the familiar scent of our own origin drifting through alien air. In truth, all of this, the Earth, the stars, you and I, speaks the same elemental language. Atoms gather, bond, and break. Energy flows. Systems find balance. Sometimes the reactions are violent, sometimes so slow they seem still, but they never cease. Chemistry is the pulse beneath existence, the thread that ties together oceans, clouds, creatures, and constellations. It's what allows a flower to open, a storm to build, a planet to breathe. And when you sit quietly, when the world outside has gone dark, and the only sound is your own breath, chemistry is there too. The oxygen filling your lungs, the carbon dioxide leaving them, the gentle fire of metabolism warming your body, all of it, a constant exchange, as old as the stars. You are the universe thinking about itself. Atoms arranged just so, capable of awe. So much of life's movement is invisible. Rocks weather, oceans mix, cells divide, and stars forge without hurry. Change does not always roar. Often, it whispers. A drop of water wears down a mountain. A molecule of carbon drifts from air to leaf to soil. A single photon escapes a sun and travels for millennia to touch an eye that will notice it. The scale shifts, but the rhythm remains the same. Transformation, equilibrium, return. That is the quiet truth of chemistry. It never stops. Even when nothing seems to move, something always does. Bonds tremble, electrons glide, particles hum their soft mechanical lullaby. The universe, in every inch of its vastness, is always busy, becoming itself. So tonight, as you rest, remember that stillness is full of motion. The air around you is alive with invisible reactions. The atoms in your blood were once light in a distant sky. And the same chemistry that built mountains and galaxies is keeping your heart in rhythm, your breath steady, your dreams luminous. The world hums beneath your quiet, patient sleep. The elements drift, the stars burn, the oceans breathe, and somewhere in that endless cycle, you are here, warm, alive, part of the pattern. Let it continue without you for a while. The universe will keep its balance. The molecules will keep dancing, and everything, everywhere, will remain quietly, beautifully alive.